Good afternoon, everyone. We're going to get an on-time start because we have lots of things to discuss. I'm Paula Mabee. I'm the Chief Scientist and Observatory Director of the National Ecological Observatory Network. It's funded by the U.S. National Science Foundation and is operated by Battelle. So I'm very pleased to be the moderator for this session, which is focused on improving critical ocean and Earth observations. And we'll be focusing our discussion on how our eyes might work together to bridge observations across these systems. Land and water are completely interconnected on our planet, but our data, not so much. And also how, with all the amazing data and emerging new technologies, we can collaborate to achieve societal benefits, especially with observed areas that hold so much of Earth's biodiversity, such as Africa. You'll have the treat of hearing from this illustrious panel of operators and funders of research infrastructure. Each of our panelists will introduce themselves and the perspective that they bring. We'll follow with so each of them will have a few minutes to do this with some slides. And we'll follow this up with about 15 minutes of discussion on stage here, and then open it up to you all for any additional questions. So thanks for coming to our session. Our first speaker is Jan Hervé de Rack, and I will leave it to him to tell you all about the cool work he's doing.
Okay. So thank you very much. Thank you for giving the opportunity to talk about this and to make new connections, of course. So I'm Jan Hervé de Rack, and I'm also the Director General of Argo ERIC. So Argo, you heard it this morning, so maybe I can already show. Okay. Well, you've heard of it this morning. Just people was talking about Argo once, and so just to say what it's all about. It's a global network of profilers. So these are floats, let's to say, that are drifting all over the oceans, and this is an initiative that is dating back to 1999, and it's because we have this specific platform that can dive down to 2,000 or 6,000 meters, and on the way up collect data, first on temperature, salinity, and then after that on some biogeochemical data of the oceans. And then it's transmitted by satellite. This is fully automated, and each of these profilers is popping up every 10 days. Okay, so it's a big network. Each of these profilers is has a 4-year, sometimes more, lifetime. And here you see the 4,000 profilers, and you see especially that it's a fully international collaboration. This means, of course, that half of it is supported by the US, but then a fourth of it by Europe and by many countries. Australia, for instance, 300 of them are in fact deployed by Australia. Okay, and well, why doing this? To answer first two scientific questions about climate change, because these are the real in situ data that you can get with such a density. It's kind of a 4D image of the ocean. You do it with ships, of course, but ships are really sparse in comparison to this network. So climate change by what is ocean heat content, but also, since we are doing these geochemical things, what is the state of this oxygenation, what is the carbon uptake, what's the acidification of the ocean, and in the end, how the ocean ecosystems are evolving. But there are also operational services, and these are, in fact, on a daily use by weather forecasting. Once you have atmosphere and ocean coupling, this helps having a better confidence in the climate, in the weather forecasting, and then in the seasonal forecasting and so forth. And it's also used for satellite validation, because that's a ground truth, so ground truth over the ocean, but that's the place where, many of this information is missing. And of course, the ocean health monitoring as a whole. let's say that there are two ways of getting our data, which are open, free from the beginning, with the FAIR principles that has been quoted also this morning. And one is really immediate, like just a 12-hour distribution with an automatic quality control, and another one with expert quality control, which is performed at least once a year. So I was not so far just talking about Euro, Argo, ERIC, because that's part of it, like I said. So if you want to have here the map, you see that there are 13 countries in Europe that are coordinated by this ERIC. And that means, in fact, 30 entities that work together in order to really fill gaps, really understand each other, make new technological progress, etc., etc. And also be the counterpart of what the other ARIs in the world are doing with Argo. And so it's an ERIC, so a European Research Infrastructure Consortium. So it's handling 1/4 of the fleet, like I said. Then, of course, we try to look at the specific European interests, which are the marginal seas. We have the Mediterranean, we have the Baltic Sea, we have the Black Sea. So otherwise, nobody would really care for that. And also, we are really willing to go into this BGC, I mean, towards this ecosystem modeling, etc., giving these parameters that are so essential, and also looking to greater depths to the abysses. And also, what is also specific is that Europe has a Copernicus system with this institute side and also the modeling side, and it's very, very unique. Satellite and regulation like this. And we develop with other marine ARIs a couple of operational tools and bricks, etc., like with ICOS, who will be talking just afterwards in the AMRIT project. And the last slide is about, so really what we are doing new, I would say, for just a couple of years, is really extending the geographical extent of the networks towards the poles and also the marginal seas and the density where you have more dynamics. The second thing is the biogeochemical variables I've talked about. And the third thing is going to do deeper and also to increase the total number of floats. Again, these are figures at the global level because we work globally since the beginning. Give the floor to Shelby now. Thank you.
Fall off. All right, good afternoon, everyone. I'm Shelby Walker. I am the Senior Advisor for Facilities and the Directorate for Geosciences at the U.S. National Science Foundation. So I have purview over all of the major facilities within GEO. That includes our ocean, earth, atmospheric, and geospace sciences, as well as our polar programs. But before I had my current role, I was a program officer in charge of the Ocean Observatories Initiative. And as it was moving through its design stage and eventually moving into construction. Let's see. There we are. So at that time, which was about 15 years ago, the OI really represented a different way of thinking about sustained ocean observations. The network consisted of fixed moorings on both coasts, as well as deep water locations, complemented by mobile assets such as gliders and AUVs. But one of the more, I'd say, innovative things about the OOI was the deployment of a fiber optic cable off the northwest coast. And that really was an opportunity to have a cable with fixed nodes and junction boxes that could then support power and bandwidth to sensors and fixed moorings. And that really provided an observation capability on a whole different scale. This approach, which was also being done by our neighbors to the north with Neptune, Canada, was just a kind of a step change in ocean observing. But as technology has evolved, the portfolio of approaches that can be done using fiber optic cables has really just grown tremendously. So a couple different things. One is now telecom cables can be deployed with sensor packages embedded in line with the telecom cables. And these support sort of just a basic set of parameters, but are really critical to understanding what is going on in the ocean. So ocean bottom temperature and pressure, as well as seismic acceleration. And of course, these variables can provide insights on things like ocean circulation, sea level rise, and earthquake and tsunami hazards. And a lot of these cables are in the process of being planned or deployed. So we have installations that are connecting Vanuatu and New Caledonia, as well as between Lisbon, Madeira, and the Azores, along with others that are being planned. And this work is being coordinated by a joint task force. And there are several that can be done, that can be seen when you look at this task force. It's under the auspices of the WMO, IOC, and the International Telecommunications Group. NSF is actually contemplating one that will connect Australia and New Zealand to McMurdo Station in Antarctica. And the portfolio of cabled observing capabilities really continues to increase. So this is the Distributed Acoustic Sensing, or DAS, which is using spare or dark fibers in telecom cables without having to have these additional sensor packages. And this has already revealed tremendous possibilities during land deployments and is now being looked at with respect to the ocean. And these fibers are really pulsed with an interrogator, and things like seismic pressure waves in the ocean, marine mammal sounds, and ocean temperature can cause small changes in the optical fiber's index of refraction. And this causes reflected light that can be analyzed through signal analysis to extract information about the cause of the reflections. Currently, there are limitations on how far along the cable DAS can be used, which is about 100 kilometers from the interrogator. But it sounds like there is a lot of research being done to extend that range. And if you look at this map of where all of these telecom cables are deployed, can you imagine being able to use these to determine what is going on in the ocean in all of these areas? So with those possibilities, of course, come a lot of the challenges, such as the immense amount of data. Data seems to be a recurring theme here at this conference. A DAS experiment that was conducted actually using the OOI cable in 2021 yielded 26 terabytes of data over a 4-day experimental period. So think about that, and then think about the map that I just put up there. And then, of course, given where the telecom cables are and what they do, there are security concerns with any use of those cables. And then becomes the bigger question of what do we do with all of that data? How can we use it to its best purpose? And I'm really looking forward to the discussion today to talk about our ocean observing capabilities and opportunities and how we can translate that into looking at new ways, into looking at the ocean in new ways. Thank you very much.
Thank you. I should have warned the organizers that I'm very prone to work accidents. And if something happens to me here, it's a work accident. Hello, everybody. My name is Emmanuel Salmon. I'm the head of strategy and international cooperation for ICOS. So ICOS is the Integrated Carbon Observation System. And in just one sentence, I tried to resume to summarize what is ICOS doing. So we are doing multi-domain measurements of greenhouse gases in Europe. So I will lift your head out of the ocean and bring some air to the discussion, maybe. Because we are also present in the atmosphere and also in ecosystems. So what you can see on the slide here is the ICOS network as it is today. So you see the map of Europe, you see a lot of dots of different colors. These colors are showing the ocean stations, which in ICOS usually are buoys or they can be fixed also. But then there are also ships of opportunities that we use to measure the concentration of CO2 in the surface ocean. The other atmospheric stations, well, these are toll towers that measure also concentrations of greenhouse gases in the atmosphere. Then you have ecosystem stations that measure the fluxes between the atmosphere and the ecosystems. So currently we have approximately 180 stations in this network and 16 European countries contributing, which means that some of the countries, the smallest ones, Hungary has only 1 station, but then Germany has almost 40 stations. So different contributions, what we call national networks. So ICOS is coordinating this, and the key word for us is standardization, because this is extremely important. You can guess from the map of Europe, which is much smaller than Australia, but if you measure something in Ireland and you give this result to the scientists, then you want this result to be comparable to what is measured in Greece also. So the standardization is absolutely key to the work we do. And you see on this map bigger dots that represent the thematic centers, the central facilities, let's say, that are serving the whole network. So the black dot over there is the head office. This is where I come from, Helsinki, Finland. So Suomi mainittu. To my Finnish colleagues in the room. And the rest, you can see, are the main places where these central facilities are. And on this complicated graph, you can just see what the purpose of this standardization is. So on the top part, you have the measurement stations, different colors for different domains. They are going through, in a way, the work of the central facilities, and all the data is made available in one place, which is the Carbon Portal, currently located in Lund in Sweden. So open, free, and fair data. These are the keywords also. You've heard a lot about that this morning. What is also important for us at ICOS is to have long time series, because if you want to follow the trends and tackle climate change issues, you need long time series. And by the way, if you want to tackle climate change issues, you could start by not cooling the rooms to 12 degrees. Sorry, but I'm freezing, even though I come from Finland. Near real-time data is also very important. So you can go to the Carbon Portal and you can check basically what the concentrations were measured yesterday in each of the stations. And quality control, of course, because we want to have high-quality data. This is the important part. So in the description of this session, there was a lot about international cooperation. And, well, this is why I'm here, not because I'm a specialist of the oceans nor of any part of the science of ICOS, but because of international cooperation. So what does that mean for us? That means a lot of common research projects together with the other environmental research infrastructures, the ENVRIs in Europe. So there has been a long tradition of these research infrastructures working together. This is the case for Argo, but there are different research infrastructures represented in the room also from Europe with whom we cooperate. And that also includes the support we provide to what we call under-observed regions, Africa being one of the examples where we try to foster collaboration also to develop an observational network. The contribution to global frameworks, so for data, the data coming from ICOS goes to bigger aggregated data that are made available then for the researchers like SOCAT for the ocean, OBSPAC for atmosphere, or FluxNet for the ecosystem measurements. But we also try to feed our knowledge, if not the data, directly into policy. This is why ICOS is an observer at COP for the UNFCCC. We also collaborate a lot with WMO, IPCC, and this ICRI is definitely a place where we try to connect with the global players. We also work on the expansion of the ICOS network, which means new stations, of course, the more the better, but also with new countries, because you've seen 16 countries are part of Europe. Even in the European Union itself, it's 27, so we still have work to do to get more countries, which means also a better scientific relevance of the whole measurement network of ICOS. And then we are also part of something that I will mention here, the Global Ecosystem Research Infrastructure, GERI, because I will take the opportunity to advertise for the side events that we will have related to that. So this is a global cooperation with 6 research infrastructures from 4 continents. And then if you want to learn more, you have the information about the side event. And I will stop here for that.
Hello, my name is Benoit Pirenne. I'm a Chief Innovation and Technology Officer for Ocean Networks Canada. Ocean Networks Canada is this organization that also, as Shelby was mentioning about OI, is providing power and communication capabilities to a bunch of instruments in the water. So we are an ocean observing system, but we have a lot of other things on our plates as well. So as you can see on this map of Canada, perhaps an unusual projection here for most of you, but most of our infrastructure is located on the west coast of the country, with small coastal observatories a little bit around the country, including the Arctic and the East Coast. With all these communities that we install observing systems in, we obviously have, in Canada in particular, a lot of First Nations and Indigenous communities that we interact with. In fact, no less than 50 on a regular basis are being engaged, and about 10% of our 160 people is composed of people whose job it is to basically interact with Indigenous communities and make sure that not only we get their permission to use their land to observe the data, but that we also respect data ownership questions, that our data is not just fair, but we implement the care principles of Indigenous data ownership and governance. Shelby mentioned the Ocean Observing Initiative in the US. South of us, there's the cable network going from Washington State and Oregon all the way to the West Coast. What you see on the map here is just north of that, the Neptune Observatory. This is an 850-kilometer cable loop that's connecting essentially hundreds of instruments under the seabed, on the seabed or in the water column from these orange squares that you see on the map here, the different sites where we provide the power and the communication capabilities. We have the advantage with this Neptune Observatory, as we call it, to basically straddle an entire tectonic plate, and basically allows us to be a completely multidisciplinary facility that addresses questions of oceanography, marine biology, geophysics, and most recently, in fact, as well, astroparticle physics, which means that we're going to be hosting a neutrino observatory at the Cascadia Basin site there. So lots more data to come as well, indeed, and truly multidisciplinary. I was on that map earlier, but I come back to it briefly here just to mention and give a few words about what's in the middle. Oceans 3.0 is the name of our data management system. It collects all the data from all our sensors, has a ton of features for data visualization, data product generation, and of course, data download or processing. Just to give you a sense as to what this means to us, obviously the product of Ocean Networks Canada is data, and we have more than a third of our 160 people or staff that is employed in the data management area. So that's also to give some pause to those who want to give a perspective of the importance of data and data management. So I'll finish by saying that we have at Ocean Networks Canada 3 goals. The first one is advanced ocean observing, and in fact, back to to the first speaker today, to Jan, we have actually also deployed for Canada a number of deep Argo floats. We continue to improve the instruments that we put in place in support of research. And in fact, further to what Shelby was talking about, we are deploying this summer distributed temperature sensing, and we will also be shortly after that deploying DAS on our network in a marinized fashion so that we can actually monitor specifically areas of interest. The number two is to develop and deliver data products and what we call ocean intelligence. So basically it's turning our raw data coming from our sensors into something that's more meaningful directly and can help decision makers. For example, one of the products that I worked on over the last few years is earthquake early warning. So we deployed instruments both on land and underwater to capture seismic events and turned that into an alert for operators of critical infrastructures in the region. And finally, last but not least, one of our strategic objectives is to work on ocean-based climate mitigation solutions. Basically, what can we implement using modern techniques, using methods such as, we can cite a few, but to basically reduce the impact of the climate by making use of the ocean. That means essentially, is there better ways to sequester carbon, CO2, using the ocean as a placeholder without harming it? So we're supporting the research, we're supporting the ability to determine whether a particular method that's being researched is actually going to be valid, working as expected, having no side effects, and being scalable. And I'll stop here.
Well, I want to thank all the speakers. That was fantastic information. And so now we're going to try to glue it together for the audience. Now it's working. Great. Okay. All right. So my first question, and we'll have about 15 minutes for questions, and we'll turn it to the audience here. My first question is basically from a global perspective. I think we know that where the earth and freshwater, terrestrial freshwater and ocean come together are some of our most sensitive, critical, and unknown areas. Swap the mic.
Hold the mic closer to your mouth.
This one seems to.
Okay, I'll start over again. Basically, from a global perspective, I think one of our big problems is that we don't have data from those junctions between freshwater, the land, and the ocean, which are very critical places and very sensitive in terms of biodiversity and all kinds of Earth's processes, sort of the dark, there's a gap. And so where do you think the opportunities are there for global collaboration? And then where do you think the challenges are? What's missing? And what, if you could snap your fingers and just have anything to sort of heal up that gap, what would it be? So I'd like to hear from each of you. Anyone want to be first?
Figure out how to turn the microphone on. So one of the things that I tried to highlight was we have these assets, these telecom cables that are just inherently cutting across that boundary. And if there's a way to be able to sort of systematically tap into those and to be able to either have our smart sensor deployment have that embedded inline sensing capabilities, or to use something like the distributed acoustic sensing that could really provide insights into that coastal margin. Given the limitations that we have on DAS right now, 100 kilometers, that is exactly that area that we would be looking at. So we do have groups right now, this Smart Cables Joint Task Force that I mentioned and bungled the name. It's the actual International Telecommunications Union, in addition to WMO and IOC, that is leading that effort. And so they are really looking at that sort of systemic way of deploying these smart sensors on the cables. But when we think about the challenges, obviously, the telecom system is very precious. It basically is our means of communicating globally, our financial systems, our security systems. So the national security implications for any country are extreme when it comes to that particular network. So if there's a way that we can somehow navigate that to tap into the scientific possibility without impacting the telecommunications capacity, that would be an enormous asset to understanding this type of this area.
All right, so what we have to realize is that whether we talk about the coastal regions or the deep ocean or anything in between, there's a lot of groups and organizations that collect data. And the way to share the data would be to start by making them fair. We've heard that many times. We continue to hear it. We've heard it for 10 years, for 20 years maybe. But it's true. Being able to take data from whether it's NGOs, government departments, research infrastructures like ours, they need to be able to share the data and bring it back to portals. And there's initiatives around that, of course. Many of you have probably heard about GOOSE, the Global Ocean Observing System. It's basically at the top of a pyramid, essentially, that collects data from different subgroups, such as the ocean observing systems of various countries. For example, in the US, it's called the OSIS, OS, with some things in the front. Canada has just started to build CIUS, the Canadian Integrated Ocean Observing System, and every country is basically contributing back to GOOSE in terms of, basically one variable at a time in a progressive way. And obviously the Argo program is a big contributor to that, was one of the original ones, but the networks that GOOSE is supporting is increasing all the time. And in fact, just recently, Shelby, the smart cables have been admitted as a new network of GOOSE. So the data will eventually, once it's all going up and operational, will also become part of GOOSE, and through that as well, going to the WMO and so on. So again, it's through the data that I think these interchanges and exchange of knowledge ultimately will take place.
Thank you. Yes, and thank you for mentioning the fact that Argo contributed to GOOSE. But then about this extent to the, I already said about the marginal seas, so it goes a little bit closer than the original Argo program. And then also there is this development of a coastal Argo, which can really go on the shelf this time, because otherwise it's really meant to drift at deeper depths. And but then, I mean, one of the issues might be also to have a secured long-term monitoring plan, because especially for this kind of instruments, the issue is the cost, and if you want to reduce the cost, you also have to provide the manufacturers with some insight of the market, in fact, because so Argo floats, it's a really niche market, but also some of the sensors that can be shared with other platforms, like with gliders or with some buoys, but still, I mean, we really need to have plans to decrease the cost. That's really a big issue. And knowing that what you're talking about, so this interface between so the terrestrial and ocean domains is a place where you have the highest dynamics. That's also a place where you really need to have a lot of instruments, because the variability in time and space is very, very, very big.
Just to add on this from the ICOS perspective, so what we try to do with the data we measure is to contribute to closing the global carbon budget. So there are uncertainties in certain areas of the global carbon budget, and one area is definitely this land-ocean continuum, where we know that we don't know enough. The current situation in Europe is that there is some kind of a segmentation of the research infrastructures depending on what they do. So we are not, contemplating this new scientific area as something where ICOS would like to be more involved, but at the same time, there are other research infrastructures present in these areas already. So the key to that is exchanging the data, having the data, as Benoit mentioned, and also a lot of collaboration between the infrastructures, because there's no point in any infrastructure developing the capacity to measure everything. So we need to take the advantage and the strong points and the expertise of the different research infrastructures.
Well, that's great. So this is pretty exciting times, lots of data, lots of new technologies. So what do you think that the opportunities are for these new technologies relative to societal benefits? So this is something that we all need to think about. This is clearly going to provide some very fundamental data to understand those interfacing ecosystems, as well as, of course, at a planetary level. But in terms of societal benefits, what comes to mind?
Okay. It's on. Okay. The societal benefits are, of course, the reason why we're doing the science in the first place, right? We want to increase the knowledge. We want to increase the knowledge not just for the sake of increasing the knowledge, though that's interesting in itself. We're doing it so that we can bring benefits directly or indirectly to society, whether it be in the form of improvements in the health of people, longevity of our lifetimes, the comfort that we have in our day-to-day lives, as well as anything that we haven't even imagined yet that will be possible tomorrow thanks to all these developments. So I think I keep repeating the same topic perhaps, but what we're getting out of these new initiatives, the new technologies that we talked about, and Shelby mentioned DAS and these other things that produce enormous amounts of data. The enormous amounts of data would take too many people to just look at them. So we're now forcing ourselves to develop machine learning techniques and artificial intelligence techniques to actually sift through the data to actually extract the knowledge. Otherwise, why did we do that in the first place? If we collect data just for the sake of it, there's no point, and there's not going to be any benefits to society. So AI will help us get benefits to society, just if only by looking for us and with our guidance at the data that we've been collecting, and perhaps help us discover new phenomena, adding to the knowledge, but obviously, again, leading to new benefits for us.
So I used to live in the Pacific Northwest of the U.S. and that very close to the Cascadia subduction zone, where the OOI is deployed just south of Neptune. And in that region, they're bracing for the big one when the subduction zone, unlocks dramatically, and they anticipate a pretty significant earthquake and tsunami. So the idea that having a cabled system there or having some kind of ocean observing system that would provide that level of warning some period of time in advance, I think is one of those elements of ocean observing that just has this sort of unquantifiable societal benefit to it. And if we think about that and extrapolate that to like the telecom systems or the smart cable deployments that we're seeing in between Vanuatu and New Caledonia or off the coast of Portugal, areas where we have this earthquake risk, being able to have that advance warning, that knowledge, is really just going to be a kind of a step change in terms of how we can prepare as a society. But one thing that I also wanted to really just mention is, when we think about the data and we think about all of the information that is coming in, how do we actually use it to the greatest societal benefit? And one of the elements under the current UN Decade of the Ocean, one of the 8 challenge areas is digital representation of the ocean. And within that is sort of that digital twin concept, where you have the virtual model of the ocean and that two-way exchange between the real world. So all of the data that's coming in, whether it's from a cable, whether it's from Argo, whether it's from ICOS, wherever, being able to have that feed into a system like a digital twin that can be sort of looked at and altered based on what people are trying to change or adapt or sort of see what's coming. One of the challenges, of course, with a digital twin model is that the observing systems should be built sort of fit for purpose for that model. So we have all of these observing systems, and how could we then translate that into something like a digital twin of the ocean to relay all of the information, whether it's earthquake hazards or sea level rise, into something that we can actually use and hopefully adjust or adapt to?
I would just like to add to this points that I was mentioning, the operational use of Argo data. Well, once something is operational, I guess that it has societal benefits, because if it's operational, it means that if you stop it, someone will really take the phone and say, why don't we have this data anymore? We can't do any weather forecast anymore. We can't do satellite, ground truth anymore, and so forth. And why should it rely on research budgets when it's so operational? So, in fact, it's good that these kind of things are confided to research infrastructures, because we make things evolve, because we are looking at new processes, because we are developing new instruments, etc. But for the part of it which is already operational, it should be supported by other funds. You see, otherwise we're really struggling between doing something always new and advanced, and I mean, in this case, why still providing these operational systems that should run on a daily basis?
So many interesting points to follow up on. We have just about nearly 10 minutes left. We'll call it 7. And this is your time. So what would you like to ask these amazing, knowledgeable experts? I see 2 questions, one up front and one in the back. I don't know who's first. We'll start with the one up front. Yeah.
I'll bring you the mic because
Oh, did I get picked? Oh. I'd given up hope. I thought someone else had grabbed it. I think someone, yes.
Thank you so much for sharing all of the amazing information. I'm from Amazon Web Services, so we're the cloud infrastructure provider for a lot of academic researchers. So I just have I'm not in the field of Earth observation, so I have a very fundamental or basic question, which is where all of you talked about, the technology adoption, et cetera, AI, machine learning models. Where do you store most of your data? Do you have on-premise data centers where you use, or are you exploring, different providers on that? And if that's okay, would you be able to share some of your challenges or the things that you hope to see in the cloud providing companies like AWS, so that we could understand this, the research needs better? And we're pretty new in the academic research field, right? So we're also learning how to better support our academic research customers. Thank you very much.
Sure.
Well, I think this will be maybe a business discussion at some point, and we can have it during the coffee break, and because my beloved boss is here, then you can even have definitive answers on that. I can just say that as I show that all the data that ICOS collects goes to one single place, which is this carbon portal. So there are things that are stored there, but of course everything is duplicated because there's no, we don't want to have things lost in any way, so that it's not everything at one single place. And of course, the whole data is also stored. So from the raw data as it is measured to the final data which is disseminated. So you can always trace back to the initial raw data if you happen to notice that there was something not right with the measurement, for instance. So this is this is part of the quality control of the whole data cycle, life cycle, because we want to have really a trace on that. But we can discuss further.
Yeah, that's great. I think we have one in the back.
Yes, please.
Yeah.
Thank you. Can you hear me?
Yes.
Yeah. Hello. My name's Adam McLeod. I'm the AquaWatch Program Manager from CSIRO. Thanks a lot for making the trip to Australia to speak to us. The question I wanted to ask is, what weight or what value do you put in emerging satellite missions and the use of remote sensing, particularly hyperspectral, superspectral, and thinking about using remote sensing over the ocean, big pixels giving you great dynamic range or signal noise ratio as well. So I guess ability to infer something about the ocean from the reflected light or whatever it might be. Thanks.
Well, very quickly, thanks for the question. Our concern is that the satellites typically can only penetrate so much depth in the ocean, from the ocean surface, and so you still need to observe the rest. So therefore, we still need to have access to the rest of the ocean using Argo floats, ocean observing systems. But we can help you with the calibration of your satellite observations from the surface.
Okay, let's take one more question, remembering that everyone's here for 3 more days, right? So make sure that you come up afterwards and take some time to find us. Yeah. Oh, wait.
You were first.
We have someone who's being passed.
That's very kind, thank you. It was a question around engaging with commercial entities. My background's Earth observation. AWS does a great job, by the way, for Earth satellite data. As you go up the value chain, you're providing an ever more refined service, a platform, wonderful, we can all build on, but it does somewhat erode commercial value, or at least in the Earth observation satellite community, a lot of companies are struggling because, well, quite frankly, the national data quality is sufficiently good, high, that it's hard to charge a premium from a commercial operation. Now, maybe this is fine. I'm genuinely curious because I don't know the ocean world. Is it okay if it's just only ever government run, as you say, and government funded? Is there a role for commercial, and if so, where does that end in the value chain as you provide a national standardized service and commercial provides the higher value that they can charge?
I think at least both in Europe but also in the US, I mean, the principle is for this kind of data to be free and so open and fair and distributed, so that in the end, of course, some downstream services can produce money. And that's our issue, in fact, that we don't get anything back directly. It's by your taxes, so just pay more taxes and then you get more data. I mean, it's totally politically incorrect, but I mean, otherwise, no company will invest in Argo floats. I mean, for sure not, because it's a tiny part of what this company would do, except if it's a righteous man in the world that does it. But even, I mean, it would have no sense really to do that. I mean, this really is something that, yes, that should be done at the governmental level, but then provided it free so that downstream services are making money, that's for sure.
And just from the ocean side of more of the operational ocean side, the integrated ocean observing system, I mean, it is government funded, but they have a lot of these regional associations that are intended to really engage with the local, the regional users and the needs that are there and help support the operation. the intent of the IU system was, how do we have the weather service, but for the ocean? And it hasn't really worked out that way. It's still very much a government-funded thing. And one of the things that we find at NSF is, in theory, and Paul and I were having this conversation earlier, we set up these systems, they serve their scientific goal, and then they go away. And if you're an operational construct, that's really hard to do. And so we always sort of have to navigate that line between have we created something that is operational and then, you know, sort of fulfills a commercial need, or how do we translate that over to a different construct?
Thanks so much. I think we've reached our time. And I want to thank all the panelists. It's been a really interesting thing to hear you all talk from your different perspectives. Lots of things came up that I'd love to follow up on. I bet everyone here feels the same. So join me in thanking this great panel. And